Okay, this is the second part of the video lecture for Math 181 for Tuesday, April 21st. If you guys recall, we're doing the substitution rule as a technique for evaluating integrals. And what I want to do now is do 3 examples of using the substitution rule. And like I said, it's a bit of an art form, so the more examples you do, the more comfortable you become. Let's say I want to evaluate this indefinite integral. I look at this and I say, off the top of my head, I don't know what the antiderivative is for this function. So I can't just use my table or what I've used before, but I think, could I try use substitution? So I'm going to try that, and I'm going to let u equal something. Now, part of the art form is, do I let u equal x, or do I let u equal 1 minus x squared, or something else? I'm going to let u equal 1 minus x squared. Okay, and then what I'm going to do is take the derivative of both sides of this equation, du dx. The derivative here is minus 2x. Then I'm going to rearrange this and write it as du over 2 minus du over 2 equals x dx. Okay. And then I'm going to take this integral here and I'm going to rearrange it as 1 minus x squared times x dx. Now, this is looking promising because I look at these two things and I say, wow, what I have here is exactly what I have here. So I'm going to substitute in for u, okay? I'm going to substitute in for x, u for x. So now I get square root, where I see 1 minus x squared, I plug in u, I get square root of u. Where I see x dx, I'm going to plug in minus du over 2, okay? And now I'm going to clean this up a bit. I can pull out the minus 1/2 here, because I can pull a constant out from underneath an integral sign. So I get minus 1/2 times the integral of square root of u du. Okay, what I've done is I've converted an integral in terms of x into an integral in terms of u. And this looks pretty promising. I actually know how to do this integral. This is a simple power rule integral. This is u to the 1/2 du. So I'm going to evaluate this. And if I do that, I get minus 1/2. Now what the rule here is I need to use that rule where I add 1 to the power. So I get u, so the antiderivative of u to the 1/2 is u to the 3/2 over 3/2, okay? And then I need to add my integration constant c, all right? And now I'm going to clean this up a bit. I'm going to multiply by the reciprocal of what's downstairs. So I get 2/3 u to the 3/2 plus c. Okay, and cleaning this up, these 2's cancel, and I get minus u to the 3/2 over 3 plus my integration constant c. The final step here is to put this back in terms of x, okay? So I'm going to substitute back in terms of x here, and I get minus 1 minus x squared over 3 plus c. And this is now this is the answer to this integral. This is the antiderivative of the function under the integral sign. Okay, that's my answer. So I use u substitution to evaluate this integral. Now let's check this. Let's make sure this is correct. If we take a derivative, of this whole thing, let's take a derivative of this whole thing with respect to x. If I do, sorry, I forgot the 3/2 power. That's my bad. There's a 3/2 power here. I forgot that. If we take the derivative here, we have we use the power rule, we have minus 1/3 times, if you use the power rule to take the derivative, so elephant to the 3/2, we bring down an elephant in front, sorry, I messed up, we bring down a 3/2 in front, and we get elephant 1 minus x squared to the 1/2 power. We reduce the power by 1. Then we go inside here and take the derivative of elephant with respect to x. That gives us minus 2x, okay? And then this integration constant c just drops away because it's a constant, and the derivative of a constant is 0. So now if I clean this up a bit, let's clean this up. These 3's cancel, these 2's cancel, these minuses cancel. And now I get, if I clean this up, I get 1 minus x squared to the 1/2 power times x. If I rearrange this, this comes out to x had square root of 1 minus x squared, and indeed, this is exactly what I had under the integral sign here, so I know that I have my correct antiderivative. Okay, this is a classic u substitution problem to evaluate an integral. Let's do 2 more examples of this. Okay, the second example is this. Integral of x cubed over x to the fourth minus 5 dx. Okay, and we want to try to perform this integral. Now again, looking at this integral, looking at this function, I don't know, off the top of my head, I don't know an obvious antiderivative for this function. And so I can't just use a simple table or what I've used previously. So I think to myself, well, could I try u substitution? Now the trick here is, what do I let u equal? Do I let it equal x cubed? Do I let it equal x to the fourth minus 5 or something else? From my experience, I know to let it equal x to the fourth minus 5. Let u equal that. And then I'm going to take the derivative of this. Du equals 4x cubed dx. Now I skipped a step here. Before I would do du dx, and then I'd move the dx to the other side. Most people who are experienced at doing u substitution don't include that step. They just kind of leave it du, and they automatically put the dx on the other side, which is totally fine. It's just skipping a little step, but it's totally valid. This is now the derivative here, and I'm going to rewrite this. I'm going to move the 4 over, so I get x cubed dx equals du over 4. Okay, and already I'm really liking this because this right here, what I found right here, is exactly what I have right here, right? It's exactly what I have there. And so this is looking like a promising u substitution integral. Now, I can rewrite this integral as this top part is du over 4. So I get du over 4 upstairs. Downstairs, I'm going to substitute u for x to the fourth minus 5. I get u. Now I can pull out the 1/4 here out of the integral sign. So I get 1/4 times integral of du over u. Okay? Now I've turned my integral in terms of x into an integral in terms of u. Question is, I'm going to rewrite this to make this a little more obvious. Integral of 1 over u du. The question is, can I find an antiderivative for 1 over u du? Can I find a function whose derivative equals 1 over u? Well, the answer to that is natural log of u, if you guys recall. The derivative of natural log of u is 1 over u. So that's my antiderivative. So I can evaluate this integral. I get 1/4 times natural log of u, okay, plus my integration constant c, okay. And then the final step here is to substitute in for, back in for x. So this integral will now equal 1/4 natural log of x is x to the fourth minus 5, okay, plus my integration constant c. And that's the answer, that is the antiderivative, the most general antiderivative for this indefinite integral, okay. Now, how do I know this is correct? Well, what I could do is take a derivative of this function with respect to x, and I should get back exactly this function here. I'm not going to do that, but I'll let you guys, if you want to do that, you can do it. And in fact, this is the correct answer. Most times when you do these, you don't need to do that final step, because most times you're sure this is right. But if you weren't sure, you could always check it and take the derivative. Let's do a third example here. And this example is a little bit different. This example, we're actually going to do a definite integral. So far we've done indefinite integrals. But in this example, we're going to do a definite integral. Okay. The good news is we can still use the u substitution for definite integrals. So look at this integral. And I don't know off the top of my head what the antiderivative is of natural log of x over x. But I think to myself, maybe I'll try u substitution. Now the question is, what do I let u equal? Do I let it equal natural log of x, or 1 over x, or something else? I know from experience to let it equal a natural log of x. Okay. And then if I take the derivative, I get du equals 1 over x dx. Okay. The derivative of natural log of x with respect to x is 1 over x. So this is what du is, and already this is looking really promising because I have this right here is the same thing as this right here, right? And so I can substitute in for u now. And so I get an integral now. If I substitute in for u, what's upstairs is u. What's downstairs is 1 over x dx is du. So I get u over 1 times du, because du is what's over here, dx over x. Well, that's just du. So this equals the integral of u du. Okay, now I've left off my limits. The reason is because now we're changing from x to natural to u. And so my limits here were in terms of x, but since I'm changing to u, my limits are going to change. I need to figure out my new limits. The way I figure them out is I have u upper and u lower. The upper limit, but now transformed to u, the upper limit for u is determined by plugging in, this now is in terms of x. I need to plug in this limit for x here. So the upper limit for u is natural log, and now I plug in 2, is natural log of 2, okay? My lower, excuse me, I wrote this wrong. This is my upper limit for u. My lower limit for u, this limit here, I obtain by plugging in 1 for x here. So u will equal natural log of 1, which equals 0. So what happens is my limits are transformed from 1 to 2. They're transformed to 0 to natural log of 2. And that's the way that works, 0 to natural log of 2, because I've changed my integration from x to u, so the limits need to correspondingly change. Okay, can I do this integral now? The answer is yes, I can do this integral. And this is simple, right? The integral of u du is simply u squared over 2. Now the question is, do I add in an integration constant? And the answer is no, because this is a definite integral. So you add an integration constant for indefinite integrals. For definite integrals, you don't. And so I don't add an integration constant. In fact, this is a number. And then I want to evaluate this integral from the limits of 0 to natural log of 2. Now another note to you guys. In the previous examples with indefinite integrals, we got our integral in terms of u, and then we substituted back in for x to get it in terms of x. And that's important to do for an indefinite integral. When we're dealing with a definite integral, we don't need to do that because we're not looking for a function of x as our answer. We're looking for a number. This is a number. It's not a function of x. And so we don't need to plug back in for x. Now, can you do this? You can do it. But most people just leave it in terms of u. They change the limits to be in terms of u. And then now we can directly substitute in these limits and figure out the number here. So the answer here now, if we plug in, will be natural log of 2 squared over 2 minus 0 squared over 2, which equals natural log of 2 squared over 2. And if you plug this in your calculator, you get 0.240. Okay? So this is in fact the exact area under the curve of natural log of x divided by x from 1 to 2. And again, we've used the u substitution rule, the substitution rule, to evaluate this integral. And again, we can use substitution rule for both indefinite integrals and definite integrals. But with definite integrals, we have to change our limits of integration and keep things in terms of u. All right, I will see you guys on Tuesday.